Hello, good morning, everyone. Just please settle down and get started in a few minutes. Just waiting for a few more people to join. Can you see my slides?
Yes, sir. Your slides are
Yeah, yeah.
visible.
Okay, cool. Hello, good morning, everyone. Again, let's get started and welcome to the brain modeling workshop. So we began this workshop series a couple of months ago. I think first one was in October, and so first time we offered a workshop on AI applications in EEG signal processing. So because we have two labs. I had two labs at IIT. One is the computational neuroscience lab, which is in biotech department. The other one is neuroengineering lab, which is in the Department of Medical Science and Technology. So based on these two bodies of expertise, we offered these workshops. So after we got first time when we offered the EEG workshop, we got a lot of response, and so we got it. So we repeated it next month. So then this time we thought we'll do this workshop on brain modeling or computational neuroscience. So this time also we got a lot of applications and probably we'll repeat it again next month. We're looking for appropriate dates when people will be available. So this workshop is an online workshop, unlike the last two workshops. It's a 5-day workshop. So these 5 days will roughly give you an outline of what we're going to cover. So today I will start with the history of computational neuroscience and how the field evolved and how is it going. And I'll also talk about a peculiar emphasis, right, that we have in my lab on I think on how this field should develop and in such a way that there'll be a lot of applications, clinical applications, and also engineering applications. So then I'll talk about some of the standard models like Orson-Exley model and spiking neuron models and so on and so forth. At the end of it, we'll be left with a very simple neuron model because we'll start with a complicated neuron model and then progressively simplify it until you have a very simple neuron model, which is called the McCullough and Pitts neuron model. And with that as starting point, tomorrow we'll start looking at small networks first with perceptron and multi-layer perceptron, then the deep networks. So deep networks generally, these are the ones which are popular, more popular in AI, and they're generally considered very artificial, so removed from brain and neurobiology and all that. But of late, people have shown that even the simple deep networks can be used for a lot of applications in neuroscience to explain a lot of neurobiological phenomena. So I'll talk about that tomorrow, and then both days in the afternoons you will be doing a lot of practical sessions, right? Implementing models and testing for yourself. Then third day we'll back up a little and we'll say that these static networks are very powerful. They can learn a lot of things, but they don't have any dynamics. So we need to have dynamical models, and with that as motivation, I'll talk about the work we've been doing on oscillator neural networks. And recently, we published a paper on deep oscillator neural networks. This is published in Scientific Reports just last week. So I'll talk about that in afternoon. You'll do a lot of projects and practical assignments on these networks. So these networks are believed to be like convenient bridge, serve as a bridge between neuroscience and AI. Right, and with this background developed for the first 3 days, in the fourth and fifth days, you will be doing small projects like half-day projects. I think you might have already selected your project. Based on that, you will be put with a separate team and you will work on that project. I think you'll be doing 2 or 3 projects those 2 days. Okay, with this background, now let us get started. Hope you can see my slides. So this PPT is on history of neuroscience. I'll talk about so the early foundations in 19th century, then mathematical models, and then the second half of last century, the computation era has begun, and then now we have a lot of modern applications and developments. So what is computational neuroscience? Basically, the idea is to describe brain using mathematical and computation models. Just like in engineering and physics, any physical object can be described using mathematical models based on the understanding of the underlying physics, the physical phenomena. So brain is obviously a physical object. It's an electrochemical organ or an object. So you can describe it using mathematics in many, many different ways. So let's talk about some of the more popular ways of describing brain function using computer models. And so if you look at ancient origins of neuroscience, especially in the Western tradition, Hippocrates, the father of Western medicine, right? So he spoke of brain as center of sensation intelligence. There was a big debate in the Western tradition about what is the seat of so-called soul. Okay, and people thought it. Some people said it's brain. Some people said it's the ventricles, which are the hollow cavities in the brain. And people like Aristotle even speculated that heart is the seat of the soul. Basically, the whole argument there is that if the heart stops, so there is no more function. It's death, sure death. Whereas if brain stops, a person can still go into coma, can be brain dead, and so on. So that's a distinction, I think. Then anyway, Aristotle's speculations on physical phenomena, a lot of them were wrong, right? Now we know that. And if you go further, just this last millennium, early last millennium, we have an anatomist like Herophilus and Galen and Vesalius who corrected a lot of anatomical studies of Galen. So that was more, hardcore study, not just speculation, metaphysical speculation about what mind is and how brain works and all, but it's like very hardcore structural anatomical analysis of brains and trying to infer what brain does based on such analysis. Then 18th, 19th century is when people started discovering the electrical phenomena. So people started realizing that brain is an electrical organ, and then with Galvani's work, it became clear that what we call the artificial electricity, which you use in the Volta cell and all that, the electrochemistry, and the electricity that you find in human physiology, which is electrophysiology, both are same, both have the same basis, right? So both electrical charges and all that. Initially, people thought the animal electricity is different. They had a term called animal electricity, which they thought is different from the artificial electricity, but ultimately they understood that it is same. Okay, one is carried by electrons, and but in biology it is ionic current. But essentially it is flow of charges. So that people understood much later. So then modeling. So Louis Lapicque proposed the first integrated fire neuron model. Although it became popular like more recently. The very first proposal came from 1907, and so he described using differential equations. The 40s saw the birth of cybernetics. Cybernetics, basically, this is right. You might have all, those of you who are from engineering, might have studied feedback control system. So basically, if you want to make the output of a certain system follow certain input, Suppose you are lifting a crane, right? You move some joystick and you are lifting a heavy weight, which will follow the joystick's movements. Right, so there is input, there is output, and then feedback from the output. If there's a gap between the intended output and the actual output, then that error is fed back into the controller and it produces some correction, and then you try to make the output follow the input closely. This is simply a feedback control system. Now imagine a system in which there are lots of inputs and lots of outputs and lots of feedback loops, all interrelated, nested. So that is people began to think at some point in the last century that human body is one such a system with brain and nerve system providing all these feedback control loops. So that field is called cybernetics, and that thinking became very strong in the last century. In the 50s, Hodgkin and Huxley in UK, they proposed the famous model of the squid axon. So they performed experiments on the giant squid axon because giant squid has very large nerves. The nerve fibers were very thick, almost 2 millimeters, compared to like about few microns in size in humans and animals, smaller animals. So they measured the action potential, although they were not the first to measure. Action potential was first measured in the 19th century by Emile Dubois-Reymond. But these people not only measured but also worked out the underlying physiology, ionic current flows, and build a mathematical model, which is what we'll be discussing today. And you will be running those codes in the afternoon and checking for yourself how it works. So these people so this is considered like broadly the first computational neuroscience model, although there were smaller models that go way back to late 19th century. So Hodgkin actually got a Nobel Prize for their work in 1963. Then since 40s, one more line of work began. So this is the simple neuron model by McCullough and Pitts. And McCullough is a physiologist and Pitts is a mathematician who is his postdoc. So these two guys got together and proposed a simple neuron model. And that was the starting point of this whole neural networks, the field of neural networks. And that was used by Rosenblatt to build a simple model called perceptron, which was developed further right in the late 90s and all to build this more popular, recently popular convolutional neural networks. Then Marr, Albus, and the cerebellar evolution. So these people propose a model of cerebellum. Cerebellum is also a very important organ in the brain. Unlike other parts of the brain, cerebellum kind of sticks out of the cerebrum, right? And it has a large number of neurons and like rich structure. So these two people propose this CMAC model of cerebellum. But more importantly, this contribution of Marr is more relevant or became very influential in those days because he proposed these three levels. So if you want to understand brain, what is the right approach? So he said you can approach them in three different levels. One is a computation level, that is, so basically the computer metaphor, like people began to apply the computer metaphor to brain function. So as to make sense of the brain. So whenever you try to understand something, you always try to understand in terms of something that you already know. And by analogy, you try to understand something new. Right here, since computer was the only intelligent system that we knew, especially in the last century, people began to apply that metaphor and you ask the question first, what does a given part of the brain do? So what is its goal? What's the objective of the computation? There's a computation level, once you are able to define it clearly. Then what is the algorithm that performs the computation? What are the set of steps, right, at the end of which you reach that goal of computation? That is algorithmic level. Then the implementation level, that is, how does the brain perform all these steps, right? So you say, okay, this part of the brain does step one, this part, then step two. Like for example, you're looking at visual system, then so let's say I'm recognizing an object in front of me. There is a mango, for example, or a cup. So so the retina does some initial processing, then thalamus does some contrast enhancement, and primary visual cortex extracts outlines, etc., etc. So my objective is to recognize that it's a mango, and the steps are first some noise cleaning, and then some contrast enhancement, then edge detection, etc. So I can define some steps. Okay, then the next question is which step is done by which part of the brain? So that is implementation. So this gave certain clarity to to the way we think about brain. But it's not always possible to split like that because the algorithmic level comes from artificial understanding of the problem, and then brain may not be solving the problem that way at all. So it can be a wrong application of computational metaphor to brain. This may not even be relevant or acceptable. But anyway, it was a very good start to use such approaches to understand brain's computations. In the 80s, dynamical systems approach became very popular, and that's becoming like gaining a lot of ground these days because that's a very profound approach to understanding brain function. So the early ideas, there's neural fields where people describe like sheets of 2D arrays or 2D sheets of unused sheets of neurons, and what kind of dynamics is possible in such sheets. To one pair of researchers who did a lot of work, Wilson and Koban. There's also Wilson Koban oscillator named after them. And Shinichi Amari in Japan also has done a lot of pioneering work on neural fields. Then Hopfield network, 1982 and 1984 papers were very influential. Also, incidentally, Hopfield got a Nobel Prize last year. Then application of chaos and oscillations in neuroscience. Walter Freeman from Berkeley is a big name in this area. 80s and 90s was declared as the decade of the brain by US government. So a lot of funding went into brain research. So that period also saw the rise of these huge simulators, very powerful simulators. So neuron genesis and multi-compartment models. And people began to build large-scale models. Like one popular example of such a large-scale model is the Blue Brain project in Geneva, right? Which is linked to EPFL in Geneva and Lausanne. So then, and again to 2000s, the fMRI is 90s has seen the rise of birth of fMRI, because with MRI you can only know the structure of the brain. If you want to understand function, how it works, you need some kind of a functional neuroimaging technique, and fMRI is one of the first and most popular, which gave a lot of insight into how things work in the brain. So that created a race to map the brain. Basically, people are put into some kind of a scanner and they are asked to perform a task, and then you see what kind of changes occur, dynamical changes occur in the brain as the person is performing the task, and that led to huge amount of work, and it's now a massive field. The reinforcement learning. So the reinforcement learning basically the field comes from psychology, animal psychology. People try to understand how animals learn to adjust their behavior, in response to the changing external conditions, and that all that animal psychology has led to developments in computation modeling. So the pioneering work in this area was done by Wolfram Schultz, Peter Dyan, and Reid Montague. So where they made a connection between the dopamine signal in an animal with the temporal difference error or reward prediction error in reinforcement learning. With that connection, then that led to a lot of development of computation modeling in reinforcement learning. Then machine learning has become quite popular in 2000. There's actually a rebirth of neural networks. In the late 90s, neural networks, the influence began to wane a little bit, but in the 2000s, after the Hinton's paper in the middle of 2000s, there's a re-emergence of neural networks, and then there's no looking back. Since then, there's no looking back. Right, all this modern AI is just emerged out of that period. So now the big question is, so how do you connect all this stuff, right, with proper neuroscience? Because AI has developed, the initial inspirations come from neuroscience, but after that, it was purely mathematical considerations that led to the development of the field. So now once in a while, people look back and say, hey, are we missing something? Should we incorporate something from brain? So then there is also connectomes era, where people started looking at network wiring structure of the brain. And so since brain has 100 billion neurons and each neuron is connected to like 1,000, 10,000 connections, it's a huge network. To work out the entire network, entire graph structure of the brain is a Himalayan task. So people began with studying nervous systems of smaller animals, like for example, C. elegans, which has only 302 neurons, is a small worm. People have worked out, mapped its nervous system completely. So, and at in case of human brain, people don't try to work out the wiring patterns at single fiber level, but at large brain region level, you have a lot of data. fMRI and something called diffusion tensor imaging, DTI, gives you those kinds of gross scale, wiring patterns. So a lot of decision-making literature, again, you have to refer back to reinforcement learning. So applied to brain structures, key brain structures, like the prefrontal cortex and mesencephalon and all that. So give rise to a huge field, and especially the role of four important neuromodulators like dopamine, serotonin, norepinephrine, and acetylcholine. So because a lot of psychiatric conditions evolve around the action of these four neuromodulator systems, right? And this is also a huge field, and people are trying to apply these ideas to understand disorders like Parkinson's, OCD, schizophrenia, depression, and so on. Okay, so some of the more recent trends, but I want to now like change gears a little bit and emphasize one aspect of comp neuro, which in my lab we have this certain philosophy of building brain models. So what is happening these days is with all this technology available, you can keep on measuring various aspects of brain at various levels, molecule level, single neuron level, circuit level, and so on. So you have mountains of data. And since we are living in the big data era, right, everywhere you talk about data sciences and data analysis, analytics. So you keep on collecting data, and with the idea that you'll understand brain at some point if you just keep collecting data. But thing is, if you just keep collecting data, if you don't have any insight into what the data means, things will just get more and more complicated, right? So, in fact, that's what is happening to some extent. So I think we need to emphasize the development of minimalist models and integrative models, which means generally models focus on one aspect of brain function, ignoring everything else. Whereas if you want to understand how brain diseases work, because if you want to fix those diseases, cure them and give patients some relief, you need to understand diseases in integrative terms, in terms of whole brain level, right? Combining different aspects of the brain and not just focus on one small part of the brain or one small aspect of brain function. So, but the problem is biology in general is very often very descriptive and focuses on details, and very often it's reductionist because people try to explain in biology, people try to explain the function of a large system in terms of the constituents. Very often you have to go down to the smallest constituent. So that's a kind of emphasis. So that makes explanation of the organ, which is brain, at systems level very hard, right? So thing is, this reductionist approach or reductionist demand is very common in biology, but in physics or engineering, we don't have that demand. We don't think that way. If you want to understand a large-scale system, an artificial engineering system, you don't have to go to the level of molecules and all. You should not, right? There is a certain intermediate level at which you can explain the underlying laws of that system very beautifully. You should not go to the smallest constituents. Whereas in biology, we have that idea that you should go to the level of cells all the time. That's when you can explain things well. So this emphasis seems to slow down progress. So there's a very beautiful article by Yuri Lazarnik, where he kind of mockingly titles the article, "Can a biologist fix a radio?" Because problem is, if a biologist approaches the problem of understanding a radio, they will immediately focus on the smallest constituent. Suppose you give them a printed circuit board of a radio. They look at all these constituents, start cataloging them, right? Okay, here there is brown cylinders and red cylinders and silver colored, right, cuboids and blue colored cylinders, etc. And then they give the dimensions. And okay, so that goes on for a very long time, right? And so that you call the structural analysis. Then they come to function analysis, which means, right, you power up the PCB and then start pulling out the components one at a time and see if there's any problem with the sound produced by the radio. So they keep doing it. Generally, in a huge radio circuit, if you just pull out some component, it may or may not affect the sound much. But imagine at some point somebody accidentally pulls out the wire carrying power into the circuit board. Then completely the sound stops. That becomes a big discovery. This is a fictionalized account of how biologists approach the problem of understanding radio. It's makes fun of it, of the whole approach. Whereas if you want to understand radio, first thing you need to know is that there is such a thing called an electromagnetic wave, right? And there is a message signal, which is also a small electromagnetic wave. And this message signal rides over a carrier wave. And that carrier wave is picked up by a tuner circuit, which is tuned to the frequency of the carrier wave. Then you demodulate it and pick up the message signal, amplify it, and feed it into a speaker. Then you get the sound. That's all. This is in essence how a radio works. If you don't have this fundamental understanding, if you just take some random circuit and keep on pulling it apart, you will never understand how radio works. It will take a very long time. So, but that's the kind of approach very often biology takes to studying biological systems. Therefore, everything looks extremely complicated and takes very long without any final conclusion, right? And so here, how do you make rapid progress in neuroscience? We have a certain kind of a philosophy and an approach to this problem. So for that, to explain that, I want to quickly take a lesson from history of science, specifically history of astronomy. Because astronomy, like all sciences, start as observational sciences because you just keep observing something and describe them, and only later you look at try to work on theories and all. So if you look at Western tradition in astronomy, Indian tradition is very different. Indian tradition in astronomy is very advanced. But let's only talk about Western tradition for now. So if you look at Ptolemy way back in first century AD, right? So he mapped a lot of stars that were visible stars known at that time, and then also mapped planets and planetary motion. He thought Earth is the center, and the other planets and sun and moon go around the sun, go around the Earth, and he described them using something called epicycles. Because when you look at another planet from Earth, since both planets are going around the sun, the apparent motion of another planet seen from the Earth looks very complicated. It will be seen as superposition of two roughly cyclical motions. Okay, such curves are called epicycles. So he used all that to describe planetary motion. Tycho Brahe also looked at something similar, but he had a mixed view. Like Earth is center of motion for Sun and Moon, but for the other planets, Sun is the center, which is a very weird hybrid model. He did that more like to achieve a political compromise with religion at that time. Then Kepler came onto the scene and he's looked at all this planetary data from for centuries. So starting from if you're talking about Ptolemy, you're talking about almost 1500 years of planetary data. He tried to fit planetary orbits into certain models. He was inspired by this platonic solids, but all those exercises didn't lead anywhere. Then at some point he kind of had a brainwave that the planetary motion could be ellipse. The planetary orbits could be ellipses. So then that clicked and that idea worked very well, and that fitted the planetary motion data very well. And then he summarized all these observations of planetary orbits into three laws. These are more like, you can say, data patterns if you want to use the terminology of data sciences. And then Newton came along and looked at these three laws of Kepler, and even he could perceive a deeper law which is behind all these three laws of Kepler. And he proposed the universal law of gravitation, where he said that there is such a thing called force of gravity or gravitational force, which is proportional to the masses and inversely proportional to the square of distance between two objects, etc., etc. So we know all that, right? That became the Newtonian revolution, because until then there was nothing universal about this observation. It just says, okay, Mars moves like this, Jupiter moves like this, right? But once Newton came along and proposed this law of gravitation, it suddenly became universal. The implication here is that even if you go to some other star system or some other part of the universe, the same laws of gravity will be applicable. Laws of gravity, laws of mechanics, according to Newton, they're applicable. That's a bold statement. So I think similarly, we should we should kind of rework the entire neuroscience into a handful of mathematical laws, then describe all phenomena in terms of those laws. For example, right now there is a kind of very important popular book in neuroscience called Principles of Neural Science. You see it on the left side. So there's a guy called David Wolpert in UK, motor science expert. he jokes about this book. So if this book is really about principles of neural science, so why is it getting fatter and fatter with every edition? Because if principles, it should be compact. Principles are always compact. Laws are always compact. So he says, no, but it's not. We haven't really got a hang of all the fundamental principles of brain function. We're still searching for them. So just like Newton has written all his laws in terms of this book called Principia Mathematica, somebody should write a book of real principles of neuroscience in mathematical terms. In such a book, again, first part will be single cell stuff, second part will be systems, right, in terms of the laws. Then the third part will be diseases, right? What happens when these systems break down. So if you look at things from this kind of fundamental laws, again, there's a lot of work to be done. And very often what is happening right now is with all this excitement and about big data and data collection and so on, we keep losing sight of these laws. We're not even looking for them because we are so excited about all this data that's generated. Whereas data is fine, but I think we need to take the trouble to get insight into what the data is saying and look for constantly those fundamental laws. And several people are saying these kinds of things. For example, V.S. Ramachandran, the Indian origin neuroscientist in US, he says we're at the Faraday stage in neuroscience. This is very early, almost like a backward stage in neuroscience. Right? That is, we don't have comprehensive theories of many brain structures. Patricia Churchland, again, a computer neuroscientist and neurophilosopher, she also says something similar. Right. So I think what we need to do is, if you want to really make progress of understanding brain at large scale, understanding disorders, there's lots disorders, what are called multifactorial disorders. We need to take a minimalist approach and develop the kind of models that are common in engineering and physics. That's when we'll make rapid progress and we'll be able to even understand brain disorders better and also treat people better. So that's the big high-level introduction to comp neuro. If you have any questions, you can just attend to them. Otherwise, I'll go to the next topic. Any questions? Sundari, how is the attendance like so far?
It's around 50 participants out of
Okay.
68 total.
Okay, cool. So if there are no questions, I'll go on to the next topic. So here in this segment, I will talk about the cellular basis of neural function or brain function, right? And so with this, then we'll start building a model in the next couple of segments. So there are two types of cells. And the brain is considered to be a network of neurons. We all know that. But there is a second category of cells called glial cells, which also have begun to become more popular since the 90s. Right? Initially, these cells were called glia because glia means glue or gum. So people thought they were just sticking around neurons and didn't have any important function. But in the 90s, people have discovered that they also are important. So let us talk about two important cell types for brain function. So neurons are relatively active. There are two things about neurons are very important. Or strikingly different, right, about neurons compared to other types of cells. One is that they're relatively active cells. Then the second thing is they have this wires sticking out of it. I'll talk about both of them in a minute and develop these ideas. The number of neurons in the brain 100 billion, but more recent estimates goes kind of downsizes it to something like 86 billion. The size of the cell body, if you ignore the wires for the moment, the cell body itself has a wide range in size, anywhere between 4 microns to 100 microns. So what is striking about a neuron? Because we can even ask a more naive question, what is special about the brain as an organ? Why do we say brain is intelligent, but we don't say other organs like heart or pancreas is intelligent? We say only brain is intelligent. Why? I mean, it's not a stupid question because if you think about it, all organs in the body are made up of cells, and all cells have pretty much like very similar ingredients, right? They all have a cell membrane. There is a nucleus, and there is a cytosol, and you have organelles like mitochondria, Golgi bodies, vessel bodies, and all these things, right? And they all share this exact same genome. We're talking about one specific organism. So many things are common about all the cells in a given body, then how come brain cells are so different, brain is so different as an organ? So if you just look at some obvious data about neurons and compare that with other types of cells, you see that we see some striking differences. One is their shape. So if you look at any other cell, you can have cells of different shapes like this, as you see in this slide. But if you look at neurons, immediately the picture changes. You have all these wires sticking out. So the cell body is a tiny little black thing in the center. I've marked it in red, right? That's like compared to other cells. Otherwise, there is huge number of wires sticking out. These wires can be very small in number. Like if you take a bipolar neuron, there is one wire on each side, okay, two wires, and at the end you can have a little branching. But on the other hand, you can have a pyramidal cell will have a lot many more wires, and a Purkinje cell you can see on the right top. A single cell can have 1 or 2 lakh connections, right? Average figure is like 1,000 to 10,000 wires per cell. So you're talking about very wiry cells. Okay, there's no other cell in the body has that kind of wiring. And given a single neuron, you can say that it's like an input-output system. It gets input from other neurons and sends outputs to other neurons. So inputs are called dendrites. They are generally shorter in length. Output usually there's one long wire, the axon, and then which branches out, and then at the end of the axon, one neuron makes contact with another neuron at this junction point called a synapse. You can see on the right side bottom. Right at that point, a signal jumps from one neuron to another neuron. So this junction point or synapse, if you take a closer look, it looks like this. So you see that when the axon of one neuron, which is like a wire basically, makes contact with the dendrite of another neuron, which is also another wire. So you can think of them as two cylinders. Right, if one cylinder makes contact with another cylinder at a side, then normally speaking, the contact area will be 0, right? But then for a signal to go from one neuron to another, which happens to be a chemical signal, you need to have some finite contact area, so interface area. So to achieve that, what nature has done is to flatten out these structures. So you see that the tip of the axon has a flattened flattened tip, and the part of the dendrite which receives this contact also has a flattened surface. So these two flattened parts meet, and there's a close interface. And this interface junction is so tight that the gap is only about 20 nanometers. So therefore, for this reason, in the early years, people couldn't even see this in the microscopes. They thought it's a continuum. There's no gap between one neuron and another. Such an imaginary tissue or a cell network is called a syncytium. But in the 1900s, people proposed that there must be a gap. They cannot be continuously connected. That turned out to be true later. So neurons are electrically active cells. What that means is any cell will have a voltage difference between inside and outside. In case of a neuron, a typical figure is about minus 70 millivolts. Outside, assuming it to be at 0 ground potential. But this minus 70 could be like minus 80, minus 90, minus 60. It depends on the exact cell type. But that's a typical figure, and that will be a constant value when the neuron is in what is called a resting state. But neuron can get excited under certain conditions. Then suddenly that voltage changes, and from minus 70, it might go even to some positive value. So let's say plus 20, plus 30 millivolts and so on, and then rapidly comes back. And and then it repetitively shows such rapid fluctuations. These fluctuations or spikes are called voltage spikes. They're called action potentials. This is first discovered in the 19th century, but like I said, fortunately, I've analyzed this and found out the underlying machinery of that. We'll work it out very soon. Okay, so when the cell neuron goes into excited state, you see these action potentials, which are just rapid fluctuations in voltage. Now, these signals, voltage signals, electrical signals, they propagate along the fibers of the neuron, just like electrical signals propagate on a wire in an electrical circuit. So now you can think of neuron as a input-output system. Inputs come from other neurons via dendrites, and all these inputs get added up because ultimately there is all these input signals, the dendrites converge on one point, which is the cell body, which is called soma. And so therefore all these signals get added up. It's called summation. And then that summation often sometimes leads to generation of these action potentials. Then once they get generated, these action potentials propagate along the axon, which is a longer fiber, like I said, and then they go to the end of the axon on the branches of the axon, which are called axon collaterals. At the end of the collaterals, these signals reach the synapse, and at the synapse, then the signal jumps across synapse and goes to the so-called postsynaptic side, which happens to be a dendrite again, and then it jumps over to the postsynaptic side. So you can see that what happens in neuron has, right, all this signaling has four components. The so dendritic processing, which is the signal coming on the dendrites, then action potential, the signal summation in the cell body and action potential generation, then the action potential propagation along the axon, signal propagation along the axon, then finally signaling across synapse, which is called the neurotransmission. Now note that all these first three components of the signaling are elliptical processes. That is propagation of signals along dendrites and summation neuron. They're all elliptical in nature. But the fourth component, which is neurotransmission, is chemical, because when the action potentials come to this end of the axon, a lot of things happen there, and that causes release of a chemical. And that chemical goes to the postsynaptic side of the dendrite and produces another electrical signal. So there is a chemical step in between. That fourth step in the signaling is a chemical step. I'll talk more about that later. So that is what is special about the brain, right? The network of neurons. And as you can see already, if you have noticed already, that these two things about neuron, that is their wire patterns and this rapid electrical signal. This is what is so special about neurons. No other cell in the body has both these properties. Okay, so if you want to understand brain, it's a large network, 100 billion neurons. Each neuron has 1,000, 10,000 connections. And not only that, this network is not a fixed network, right? These connections can make and break very fast at the even time scales of tens of seconds. The thing is, the gross anatomy of the brain changes very slowly over the years and decades. But microanatomy, if you look at the connection patterns at microscopic level, they change at a much rapid time scale. So whenever you learn new things or forget old things and so on, these changes are happening constantly at level of your synapses. So that can happen order of tens of seconds. There's another kind of synaptic change which happens even faster, like millisecond level, which is just a functional change in the connection. That is, connection is physically there, but its strength can change with time, and that can happen over the time scale of milliseconds. So you're looking at a very large, complex, and highly variable or a labile network. That's what brain is. And even if you compare this with the entire mobile network of the world, where you have about 5 billion mobile connections right now, and 100, let's say 100 contacts per mobile, that is still a much smaller network than brain's network. So that's what is so special about brain. That's why brain is so powerful. Then the second kind of cell, glial cells, initially people thought they are 10 to 50 times more in number, but more recent estimates say that they're about equal in number to neurons. They support neural function in many ways. I think I'll skip some of this, not very important here. Then let us look at signaling a little bit more. Like I said, these waves propagate over the dendrites and axons. Is there some difference between the manner in which these waves propagate over dendrites versus axons? In dendrites, typically when the signals propagate, the propagation is lossy. What does that mean? The amplitude of the signal goes down as it propagates forward. Whereas when it propagates on an axon, right, it is not lossy. The signal is, the same action potential marches along intact as it goes along the axon. So it looks something like this. Okay, so the lossy signals from the dendrite get added up in the soma, and there in the soma, the action potential is generated. And once it is generated, it nicely marches along the cable without losing amplitude. And the way the action potential is generated in the soma, or specifically this part of soma called axon hillock. So what happens there is, if I inject some current into the axon hillock or into the soma, right? If the current amplitude crosses some threshold, that's when the action potential is generated. So suppose I give a small current. See, this plot shows the input and output, or the stimulus and the response. In the bottom, we are seeing the input current amplitude, and the top you are seeing the voltage response. If the current amplitude is small, voltage response is also small. Now you gradually increase the current amplitude, voltage response also gradually increases. But this happens only up to a point. Once the current amplitude reaches some threshold, suddenly something happens in the neuron, and you see a huge voltage response. And that once that happens, there is no stopping. So it goes all the way to some positive value and comes back down. And so this process is called depolarization, because the normal polarity of the neuron is negative voltage inside. But once the action potential is generated, once neuron is excited because of the stimulus like this, the polarity flips and voltage inside becomes positive, like you see in this picture. So this is called depolarization. So finally, when you go to the last step, neurotransmission, like I said, it's a chemical step. So now if you take a closer view of the synapse, the action potential comes along the axon, reaches the presynaptic terminal, and at the terminal, a lot of chemistry takes place. And this arrival of AP causes release of a substance called a neurotransmitter. So right, we'll take a closer look at that. And then the substance comes to the postsynaptic side. Again, a lot of chemistry takes place here. That produces another voltage signal on the postsynaptic side, and that is called postsynaptic potential. For obvious reasons, it's a voltage signal or a potential produced on the postsynaptic side. Now, in some cases, this potential on the other side, the postsynaptic side, is a positive wave. In some cases, it's a negative wave. So if it is a positive wave, we call it excitatory postsynaptic potential. If it's a negative wave, we call it inhibitory postsynaptic potential. And in a synapse that produces EPSP, or excitatory potential, is called an excitatory synapse. And a synapse that produces inhibitory potential or a negative potential is called inhibitory synapse. It all depends upon the chemistry of synapse. I'll explain that in the next segment. Okay, so depending upon the postsynaptic side, you can have even if it is high EPSP, it can be a high EPSP or a small EPSP, like you see here. Or an IPSP also, it can be high IPSP or a low IPSP. Right, this high or low leads to the concept of synaptic strength. Right, that means a given synapse can produce a very strong response or a weak response. Now, the current thinking in neuroscience is that the information that we learn when we learn a new skill or learn a new piece of information, that's somehow encoded in the form of the synaptic strength. Let's say you can associate a number to the synapse, and say the strength of the synapse is this number. Right? If the number is small, the response is weak. Right? The number is big, the response is high. And when you learn, this number changes. So think of a number associated with every synapse in the brain. So it's a huge network of synaptic strengths, right? And this network is what represents information in the brain. There's no separate RAM or anything in the brain. It's all distributed in terms of these synapses which are all over the brain. And the synaptic strength is a placeholder of information in the brain. That's the current thinking in neuroscience. So like I said, the two kinds of synapses. Now, to summarize everything, like I said, there are 4 different components, and all the signals come from different neurons, get added up. And you have sometimes some synapses are excitatory, some are inhibitory. So if excitatory synapse, you see that in this picture, I have this orange neuron, which is an excitatory neuron, sends out an action potential, which comes to this yellow neuron. So this synapse is a excitatory synapse. So it produces a EPSP, a positive potential here. Then consider this blue neuron, which releases another action potential, which comes to the synapse here, which is an inhibitory synapse. Therefore, it creates an IPSP. So one neuron is creating an EPSP, another neuron is creating an IPSP. Both get added up. And if the net result is still positive, then the yellow neuron produces an action potential, which then propagates down the axon. So this kind of an addition of all the inputs, which is done by this yellow neuron, it's called spatial summation. There is also different kind of summation called temporal summation, which works like this. You see, a given axon can carry multiple action potentials at the same time. They come one after another quickly. So when the first AP hits the synapse, so it produces one PSP. By the time that PSP dies, the synapse is hit by the second AP. See that in the picture at the top. Then by the time the first two die, it's hit by the third AP. Okay, so because of this, because PSPs are slow waves generally, action potentials are very fast. They are typically only about 1 millisecond long, but PSP can run into hundreds of milliseconds. Therefore, they get added up, and you can have a huge wave because of this. And this kind of a summation is called temporal summation, summation through time. So now to summarize how a neuron works, a given neuron gets inputs from many other neurons, and some inputs come from excitatory synapses, some come on inhibitory synapses. You add them up all, and if the total sum is less than some threshold, then neuron doesn't get excited, so there is no action potential generation. If the total sum is more than some threshold, neuron gets excited, there's action potential generation. Then the action potentials, right, generated from here, from the soma, propagate down the axon, go to the end of the neuron. So then they get circulated. Okay. So that's all. That's just quick overview of how signals are generated. But in the neuron, I didn't go into the details of the molecular machinery which generates the signals. So we'll take a short break, and I'll look at the molecular machinery. And after that, we'll be ready to uh, build a Hodgkin-Huxley model. So Sundari, should we take a break now or after the
So we
next?
no, we can take a break now. So until 11.
Okay, so 10:50 now. So we'll meet at 11 again. We'll continue at 11 again.
Thank you, sir.
Thank you. Okay, so let's continue.
1 second. Some participants were wondering if you could be a little louder.
Okay,
Thank you.
is it better now? Can you hear better now?
I can, sir.
Okay,
Yes, sir. I think you can.
yeah. So let us get going. In the last segment, we talked about neural signaling. I talked about all the four components of neural signaling. So now we'll talk about the molecular basis of this, because that's what you need if you want to build a computation model. So we'll review the same four components, but at looking at the molecular chemical basis of these four components. Again, the four components are the same. So here we are talking about the generation of membrane potential, generation of action potential, then axon propagation and neurotransmission. So we already seen that you have this resting state, right, which is at minus 70 millivolts, and when it gets excited, in the excited state produces action potentials, the APs. Now, how are these signals generated? So the first thing we need to understand is that the cellular medium is an electrolytic medium. Cytosol is filled with some kind of electrolyte. There are a lot of ions. These ions, both inside and outside the cell, there is an ionic medium. A lot of important ions playing an important role in the neural signaling. The four major key ions are sodium ions, potassium, chloride, and calcium. Now, these two ionic media inside and outside of the cell are separated by the membrane, which is a lipid bilayer membrane, right? And it's an insulating sheet which separates these two media. Now, the ion concentrations in these two sides of the membrane are at different levels. So, for example, this table gives you the typical numbers. So, inside the neuron, that is in the cytosol, sodium ions are at 15. The typical figures, it depends, varies on from cell to cell and also based on the situation. Inside, sodium is 15 millimolar, outside is 150 millimolar. And potassium inside is 150 and outside is 5.5. So basically, sodium is low inside and high outside under resting conditions. And potassium, it's other way around, high inside, low outside under resting conditions. Chloride is 9 millimolar and 125 millimolar outside. Calcium is very low inside. So we look at it's, I can't see this here. Yeah, so 10 power minus 4 millimolar inside and 1 millimolar outside. So calcium is extremely low inside. Now, each of these ions has a valence, right? Sodium, potassium have valence of +1, and chloride has a valence of -1. Calcium has a valence of +2. So the lipid bilayer membrane itself is an insulating sheet, and the ions cannot cross through the membrane directly. So if they have to cross the membrane, that happens through special pores called ion channels. These are basically proteins, the membrane spanning proteins, which cut across the membrane and forming a small pore inside them. And the ions can go through this pore. And typically, different kinds of ion channels permit the flow of different kinds of ions. Therefore, very often they are named after the ions which they permit passage. It's also not always true, because some channels can permit multiple ions, but simple thumb rule is like a one-to-one relationship. So therefore, often named after the ions which they allow passage. Like, the sodium channels are the ones which allow passage of sodium ions and so on and so forth. Okay, and therefore the ions are selectively permeable. So the ion channels are selectively permeable to corresponding ions. And then these ion channels are not constantly open. They open and close. That open and close dynamics can be controlled by various factors. And this process of changing the channels, opening and closing state of the channel, it's called channel gating. So there are multiple mechanisms of channel gating. Two mechanisms which are very important for neural signaling are voltage gating and ligand gating. So in voltage gating, based on the voltage between the two sides of the membrane, the channel can open or close. So, for example, in some cases, when the voltage is increased, channels open. In some other cases, when the voltage is decreased, channels open. But anyway, the change in voltage can cause this open close state change of the ion channel. That's called voltage gating. In ligand gating, the ligand is basically some kind of a chemical, a molecule. When this molecule comes and binds with a receptor which is linked to the ion channel, then that binding event causes open close state change of the ion channel. Okay, so that is called ligand gating. Now, how is this voltage signal generated in the neuron? So for that, we need to go back to your electrochemistry, which you might have studied in your +2 or I don't know, high school chemistry. Take, for example, a beaker having some kind of electrolyte like potassium chloride. I imagine there is a membrane separating the two compartments of the beaker, left and right. And left side you have high KCl, high concentration KCl. Right side you have low concentration KCl. If the membrane is permeable to both the potassium and chloride, right, then both these ions or ionic species go from left to right, and this flow keeps on going until the two concentrations become equal. So nothing interesting happens at the end, and this whole thing becomes uniform and homogeneous, so nothing interesting happens. But consider what happens when the membrane is semi-permeable. That is, it allows passage of only potassium but not chloride. So then what happens again, since there is high concentration of potassium on the left side compared to right side initially, potassium ions keeps flowing from left to right, and that creates a positive charge buildup on the right side because both compartments are initially electrically neutral, right? And the only thing that is different between two compartments is the KCl concentration. So therefore, since the concentration goes from high to low, potassium goes from left to right. Chloride cannot go from left to right because the membrane is not permeable. Therefore, there's a buildup of positive charge on the right side. So voltage on the right side starts building up compared to left. So then that will create a current going from right to left. So you see that there is a chemical gradient acting from left to right because of the concentration difference. And that causes the buildup of an electrical gradient acting from right to left because of buildup of positive charge on the right side. So at some point, these two tendencies or forces perfectly cancel each other. Right? At that point, the flux stops. And by that time, already some potassium would have got accumulated on the right side. That creates a voltage on the right side. So you see that because of this arrangement, you start with a high concentration on the left side and you end up with a high voltage on the right side in under equilibrium conditions. And that voltage is given by a formula, which is called Nernst potential, is given by this formula. So V1 minus V2 is equal to RT by ZF times ln of X2 by X1. X2 is the equilibrium concentration in the compartment 2, and X1 is equilibrium concentration in compartment 1. R is ideal gas constant, T is absolute temperature in Kelvin, F is Faraday constant, and Zx is the valence of the ion. So with this formula, you can calculate the Nernst potential. So this you can now with this formula you can separately calculate the Nernst potential because there are multiple ions, right, in the neural media. You can calculate this for different ions. So if you take sodium values or let's say potassium values, potassium is low outside, high inside. So the typical figures again. If you plug them in, you get potassium Nernst potential or EK, which is minus 77 millivolts. And the ion channels also have certain conductance because it's just a pore which is allowing passage of current, so therefore it has to have some resistance or conductance. In these neural models, we prefer conductance because what happens is all these channels sit across the same membrane. So theoretically, they are all in parallel, they form a parallel circuit. And in a parallel circuit, if you want to add up resistors, it's easy if it is conductances and not resistance, because if you remember the resistance addition formula, in series resistance, just R1, R2, R3, R1 plus R2 plus R3, etc. In parallel, if the combination is like 1 by 1 plus R1 plus 1 plus 1 by R2 and so on and so forth, right? So it's a formula becomes complicated in parallel circuit, right? It's difficult to add resistance. But if you have conductances in parallel, you can simply add the conductances G1 plus G2 plus G3. So therefore, since all these channels come in parallel in the membrane, right, it's typical to represent them in terms of conductance and not in terms of resistance. So typical conductance value for potassium is Gk is equal to 36 millisiemens per centimeter square. So therefore, you can think of a given potassium channel as an equivalent circuit of that. You can think of it as a series between a certain conductance value and a battery. Battery corresponds to the Nernst potential, Ek. Similarly, if you look at sodium value, sodium is high outside and low inside. If you plug them in, you get ENA value as 50 millivolts and GNA value is 120 millisiemens per centimeter square. So if you combine them, you can think of a sodium channel, right? In electrical terms, you can describe it as a series between a conductance and a battery. Now, so in neuron, the key channels which produce the action potential and all this rich dynamics of electrical activity is these two channels, the sodium channel, potassium channel. Particularly, you see that in this picture, we have drawn an arrow cutting across the conductance. What that arrow means is that the conductance is not a constant, it is time varying. Okay, and here also we've done an arrow across the conductance. What that means this Gk is not constant, it's a time varying quantity. So so this variation of conductance happens as a function of the voltage itself, membrane voltage itself. So that what that means is these two channels are voltage dependent channels. So we talked about two kinds of channel gating, right? Voltage gating and ligand gating. So this arrow represents that these two channels are voltage gated channels. In fact, this voltage dependence of the channel conductance, that's what gives the neuron all this rich dynamics of action potential generation, all that. We will see all that in the Hodgson-Huxley model. Now, in the simplest neuron model, the Hodgson-Huxley model, these two channels are voltage gated, but all other channels are not voltage gated. They are voltage independent. That means they are constant conductances. There can be many of them. So you can think of each of those channels also as a combinations of, right, as of certain conductance and certain battery. Suppose you have some chloride channel. You can think of some conductance for that and a Nernst potential for that. You can apply them in series like this. Or you can have other sodium channels which are not voltage dependent but voltage independent. Then again you have other branches like this. So imagine you have a lot of channels, all of them are voltage independent. Right, each of them has a series of conductance in the battery. Then from electrical circuit theory, there's something called a Thevenin theorem, which says that if you have many such elements and all of them are constant, then you can simply combine them and represent them as a series between a conductance and a battery. That's what the Thevenin theorem says. Mm-hmm. So to simplify the circuit representation of the neural membrane, we are simply replacing all these possible ion channels by simply one branch which has certain conductance and a battery. So now if you combine all of them, right, you get something like this. There is one branch corresponding to sodium channel, one branch corresponding to potassium channel, another branch which corresponds to all other voltage independent channels, whatever they may be. I'm not interested what all are present. I'll just combine all of them into just one branch. In addition, there is a fourth element which we have ignored, which is the membrane itself. The ion channels are stuck inside the membrane. They are protein structures inside the membrane. We have given representation to each of them, but membrane itself is an electrical element. It's a capacitor because it's a two sheets, right, of lipid layers, right, in parallel, which is insulating. So it's like a capacitor, parallel plate capacitor. So membrane itself is represented by a capacitor here. So this is a circuit model of the membrane. So with this, we should be able to understand. So if I inject a current into the neuron, how does the voltage change, and how does it produce action potentials. All these things you are able to understand from this circuit model. So let's now try to, before we write down the equations and do a more serious analysis, let's try to intuitively understand what's going on. So let us consider the circuit under resting conditions. That means under resting conditions, all the voltages and currents are constant. So then what happens, when voltage is constant, then the capacitive current is zero, because current here is C dV by dt. So V is constant, so current is zero. So you can remove the capacitance for the resting condition. Then you have only these three branches. Then if you calculate this using simple circuit theory, you will get the membrane voltage, which is Vm, is equal to this formula. The simple circuit theory, Kirchhoff's laws are applied to do this. Now in this formula, now consider two cases. So what happens is, under resting conditions, potassium channels are open and sodium channels are closed. Under excited state, opposite things happen. Potassium channels are closed and sodium channels open. So if you insert that assumption into this formula, let's see what happens. Potassium channels are open, which means Gk is a big number compared to sodium channels are closed, so Gna is a small number. And we also assume that Gk is bigger than Gl. So all these other ones which are voltage independent channels, we call them leakage channels because they constantly leak current. So they're called leakage channels. So if you assume Gk is much bigger than the other two kind of conductances, then in this formula, so Gk, the term having Gk is bigger than other two terms. So then this whole formula reduces to this Gk Ek by Gk. So then what happens? Gk gets cancelled, you get Ek, which means when Gk conductance dominates other two conductances, the Vm, membrane voltage, is very close to Ek, and Ek happens to be minus 77 millivolts. So Vm is close to minus 77 millivolts. Right? Actually, under resting condition, it is not that low, but about minus 70 millivolts. It's close to Ek basically. Now, in the excited state, let us assume that potassium channels are open, sodium channels are closed. Sorry, other way around. Sodium channels are open, potassium channels are closed. Then what happens? Gna term dominates the summation. So numerator becomes like Gna Ena approximately. Denominator is just Gna. Then the whole thing is equal to Ena. Ena happens to be like plus 50 or something like that. Whereas so VMA is like close to plus 50. Actually, VMA goes up to like plus 30 millivolts or so. So basically, even if we don't do a detailed analysis of the circuit, which is much more complicated, if we just do this, quick back of the envelope kind of calculation under resting conditions, we can see that if potassium channels are open, the voltage is negative and close to Ek. And if sodium channels are open, potassium channels are closed, then the voltage becomes positive and goes close to Ena. Okay, so if you want to take the membrane potential up and down, you basically play with sodium-potassium channels. If you open potassium, voltage goes down. If you open sodium, voltage goes up. These two are like two knobs to control the membrane voltage. So when you now try to excite the neuron by giving pulses of current, when you give a small pulse, right, so when you give a current pulse, so that will create a small increase in voltage. And increase in voltage will make sodium channels open. And that will in turn, because we know that when sodium channels open, that will increase the voltage, that will in turn increase the voltage. But that increase in voltage will also increase open potassium channels. But the thing is, when potassium channels open, voltage goes down. We have seen that already, right? And that will then again close down potassium channels further. Okay, and so because of, you see that the response of sodium and potassium to this initial increase in voltage, which is created by the injection of current, is opposite. Okay, so these two processes also operate at different time scales. The whole thing is a bit complicated. I'll have to now get into equations. These two interacts, and then because of this, you have this response where you have a rapid increase in voltage and rapid fall in voltage. Rapid increase in voltage occurs because of opening of sodium channels, and rapid fall in voltage happens because of the subsequent opening of potassium channels. So that's how the action potential is generated. And this rising AP is called this part of the action potential is called the rising phase. The voltage is going up towards positive values. After that, it goes down. That's called the falling phase. And as it falls, it not only goes up to the resting state of -70, it even goes below that, right? And below that, that's called hyperpolarization phase. That means the normal polarity is negative inside at -70 millivolts at resting state. But at the end of AP, what happens it goes even further negative than -70. That means it gets more polarized than normal. So that's called hyperpolarization. So it is this phase. After that, it comes back to basic resting value, -70. And then if there's further current stimulus, it will again continue. The same thing continues. The best analogy to this is, unfortunately, it's not a very pleasant analogy. It is a toilet flush, a very familiar toilet flush. I don't know if you have time to play with the toilet flush ever. I mean, you can really get a feel for how a neuron works. In toilet flush, if you turn that knob a little bit, if you move it only slightly, there's little leakage of water and then it stops. But if you move the lever completely down, after that, there's a huge, flush of water. And once that starts, you cannot stop it again. It's very hard to stop it. It will go on until the entire tank is emptied. Roughly, you can imagine that's how a neuron works. That's how neuron's charge gets discharged, right? And then gets ready for next discharge again. So all this was worked out by Hodgkin and Huxley in their famous model. And so when you give these input current pulses, up to a point, there's a proportional rise in the voltage. But after some point, once a threshold is crossed, suddenly it gives a huge response. So you see that the current voltage response of a neuron is highly nonlinear. You can think of it as almost like a step response. That is, up to some point, very slow linear increase. After threshold, suddenly there is a nonlinear rise and there's a huge increase in response. And this response is called all or none, right? That is almost like a step-like response, right? And then when you come to neurotransmission, we have seen that there is a chemical step neurotransmission. So in this process of this chemical signal, the three major molecular players. The first is when the AP comes to the presynaptic terminal, it causes release of a chemical which is called a neurotransmitter, NTS. This neurotransmitter, once it releases from the presynaptic side, it diffuses across the small gap called the synaptic cleft. And on the other side of the gap, this chemical binds with a receptor, another molecule, which is typically a part of the ion channel itself. So it binds with that. And this binding event causes opening or closing of an ion channel, depending upon the type of the receptor and all that. So that is shown in this picture. So you see that the neurotransmitter molecules are packed inside these small packets called vesicles. When the AP comes here, that actually leads to certain molecular events, and I'm not going to all that, and which causes these vesicles to start moving towards the membrane, towards synaptic membrane, and then they bind with the membrane and release their contents into the synaptic cleft. Inside synaptic cleft, these molecules diffuse and reach the other side, and they bind with the receptor on the ion channel. That binding event opens the channel, and then current flows into the channel, and which causes increase or decrease in the voltage on the postsynaptic side. So this picture shows all three molecular players, neurotransmitter, and receptor is just a part of the channel itself in this case, and that binding leads to opening of the channel, and current flows in and voltage changes. Now, there are two types of receptors, maybe not very important in this context, but I'll quickly mention it. There's what are called inotropic receptors, where the receptor is part of the channel itself. And there is a metabotropic receptor, where the receptor is separate from a channel. So here the neurotransmitter binds to the receptor. This is a receptor. And that causes a lot of, say, signaling, a series of signals, what's called signaling cascade. And these signals then activate the channel and so on. The only thing, these two steps are separated in the metabotropic receptor. Now, I said there are two kinds of synapses, excitatory and inhibitory. In case of excitatory, the difference comes from the exact molecules which play a role. In case of excitatory, typically the molecule that the neurotransmitter used is glutamate. In case of inhibitory, neurotransmitter used is called GABA. And the channels that or ions that play a role also different. In case of excitatory synapses, the ion channels that are involved are sodium channel because that's what causes increase in potential on the postsynaptic side. In case of inhibitory synapses, it's either potassium or chloride. In case of potassium, the potassium goes from inside to outside. As a chloride, chloride goes from outside to inside. But in both cases, the result is same. Then potential becomes negative. Okay, and then the receptors of this also there are multiple receptors. Right, glutamate has multiple receptors. GABA has multiple receptors. I'll skip all these details. So here we have to look at the concept of synaptic strength, like I said last time. Because at a synapse, the input to the synapse is simply the action potential. The output is a PSP, but the action potential is always it has a fixed size and shape. That's what is beautiful about action potential. It's like an atom. It's always fixed in size and always goes from negative to positive. But the PSP is not like that. PSP is graded. AP has fixed amplitude and fixed duration, whereas the PSP is more graded. It can have variable amplitude, variable duration also. And the size variation, if the size is big, then you call it a strong synapse. If input is same, response is much stronger, then you call it a strong synapse. Whereas if the size of the PSP is small, you call it a weak synapse. So this gives us the concept of strength of a synapse. So this strength varies with time, and this can varies as a function of learning. So that variability in the synaptic strength is called plasticity or neuroplasticity. And because brain is able to learn information, and that's because of this neuroplasticity. Okay, so we have again to summarize, a given neuron can get inputs from many other neurons. If the negatives dominate, then on the whole, the neuron voltage is still negative, so there's no action potential. If the positives dominate, right, then the voltage goes up, crosses the threshold. That's when the AP gets generated. Okay, so now you can think of the neuron as some kind of a step-like device, right? What it does can be described as some kind of a thresholding operation. If the total input is less than a threshold, the neuron doesn't respond. The total input is greater than some threshold, it responds. It has a step-like response, and this nonlinearity is very crucial for its computing functions. So with that, we have covered basically the molecular basis, right, of neuron signaling. Now, with this basis, now we'll go ahead and look at right how Hodgkin-Huxley model can be formulated. Okay, any questions so far? We will change gears and go deeper into a mathematical model.
Hello,
sir.
sir.
Yeah, please go ahead. Yes, if you want, I'll
Yeah.
stop sharing for a second. And yeah,
Hello, sir. First of all, thank you for the lecture. And I just have one small quick question that in your initial slides, you were showing that out of cytosol, the voltage is 0. So I just wanted to
No,
understand that
outside.
why is it? Yeah, yes, sir.
Yeah, it's only like a ground potential. It's only reference value. If you take outside to be 0, with respect to that, inside is -70. What is
Okay,
always
sir.
measured as difference between 2 points. There's nothing like absolute voltage in it.
Okay, okay.
And that's a
And sir,
convention.
okay, sir. Okay.
Yeah.
So just another question is this, that when you were showing the circuit with each batteries of GNA, like sodium, potassium, and chloride, is it the reduction of all the sodium into a single battery, or do we have many circuits when we
No.
represent it?
So that circuit, very good question. The circuit, let me share the screen again. That circuit represents actually a membrane. So this one, right? You see the circuit.
Yes, 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 sir.
So the circuit actually represents a small patch of neural membrane, doesn't represent the entire neuron.
Okay.
Okay, so imagine a small patch of the neuron where within that patch the voltage is uniform everywhere. Right?
Mhm.
Then how do you describe that? So that's what the circuit represents. But if you look at a real
Oh.
neuron, it's a lot more heterogeneous. So voltage in one point can be different from voltage in different point. Okay, but the circuit represents only, it's a model of not full neuron. It's a model only of a small patch of the neural membrane. Is that what you're asking?
Yes, sir. Sir, it's clear. Thank you so much. Thank you.
Yeah, so yeah, it's not a model of a full neuron. It's only for a small patch of membrane. So the assumption here is imagine an infinite membrane, okay? Infinite sheet of membrane, I mean some hypothetical sheet of membrane, and separated by cytosol on one side and extracellular space on the other side. All right, and then since infinite sheet does and everything is homogeneous, what is same everywhere? There's no spatial variation of voltage. In that kind of ideal situation, what is the dynamics like? That's what this circuit is representing. If you want the model of a real neuron, then you have to have all the heterogeneity. You have to put in the neuron geometry, and it gets very complicated. But that's the kind of thing you do in compartment modeling. So in compartment modeling, you assume that a neuron is like a cell body is like a sphere, right? So what is called as a spherical capacitor, right? And then every fiber now becomes, you can represent all these wiring patterns or wiring structures as a series of cylinders, right? And then it becomes a cylindrical capacitor. So like that, you approximate the different parts of neuron by different geometric idealization, right? And then you can give a circuit model for each of these geometric idealizations and connect all the circuits, and you have the circuit model of the entire neuron. Right, that's the next step. But right now we are just looking at a very simple case, which is just one small patch of neural membrane. Okay.
Yes, sir. Thank you.
Any other question before we go on? Because now we'll go deep into like a deep dive into the circuit dynamics.
Hello,
Yeah.
sir, can you hear me?
Yeah, go ahead.
Yeah, thank you for the course. I find it really exciting. I had one curious question. What happens if the EPSP or IPSP are not produced enough, like the GABA or the glutamate?
Then there is no response on the postsynaptic side. That's all.
Okay, like does it affect functioning of the human body or something like
No,
that?
I mean you're talking about one synapse, right?
Okay,
So in one synapse, if there's no EPSP, IPSP, nothing much happens. So there'll be thousands and millions of other synapses.
okay.
No, are
Sure.
you saying all over the brain there is no EPSP? That's not possible. Then it's a brain dead.
No, sir, I'm asking if there's like now we are saying like gender optimal conditions, right? I'm asking what happens if it's produced less or something like that.
So in a given synapse, if the EPSP, IPSP is small, all that means is that synapse is a small, weak synapse,
Okay, fine.
right? So basically, the information in the brain is present in the pattern of the synaptic strengths. That means some
Okay.
synapses are strong, some synapses are weak. Right now, at this instant in the brain, some are strong, some are weak, and that pattern of the synapses is what is present information present in the brain. See, imagine suppose you have a computer file on a hard disk,
Mhm.
right? Some bits are ones, some bits are zeros, right?
Okay,
So the
yeah.
entire pattern of ones and zeros is what represents the information.
Yeah, okay.
If all bits are ones, it is useless. It doesn't carry any information.
Okay.
So like that, some synapses have to be strong, some have to be weak. That's when there is a variation, and then there's information.
Okay, fine.
But that keeps changing. Just like when you rewrite a file, some bits become one, some bits become zero. When you write fresh information to the brain, some synapses become stronger, some synapses become weaker, and then you have new information.
Okay, sir. Thank you.
Very good. I really enjoy this question because that's what is, because you can always watch videos on the internet and all, but in a live lecture, that's the thing, that's the advantage, right? You can ask questions and get clarification. If I know it, I'll explain. Otherwise, I'll have to refer to some book or something. Please, chat box, there was some comment just now I'm seeing. I can't see the messages. Are there any questions in the chat box?
No, sir.
Okay, fine.
No.
Any other questions, or shall we continue? Okay, so let us continue. So until this point, we have basically we have constructed this equivalent circuit, right? So it's a very simple electrical circuit, but the complication in the circuit is that nonlinearity. The CC, that arrow cut across, that cuts across the two conductances. That's where all the fun and games is, right? This conductance is a function of the voltage Vm itself, and that's what makes the circuit dynamics very complicated, also very useful. So let's see how that happens. So in this circuit, you all know the Kirchhoff's current law, right? That is, the total current going to a given node is equal to 0. So which means in this case, you can inject current from outside into the cell, and that gets split across these four different branches: the capacitive current, sodium current, potassium current, and leakage current. So that is shown in the simple formula. External current injected into the cell gets split into four parts in these four branches. Okay. Now, these four branches can be written electrically like this. Capacitive current is C dV by dt. Sodium current is basically, if you look at this, the voltage here is Vm. So Vm minus ENA times, that is this voltage, times GNA gives you the sodium current. Okay. Similarly, you get Gk times Vm minus Ek. That gives you potassium current. Similarly, Gl times Vm minus El. That gives you leakage current. We add up all these four terms, that gives you external current. Okay. This is a basic equation. So now, the main thing is, this is a simple linear circuit. Had GNA and GK be constant, you see that in this circuit, GNA and GK are not constant; they are variable. How are they variable? Because they depend on the voltage Vm itself. That makes the equation highly nonlinear. So how does it work? So to understand it, we need to understand the channel dynamics. So we said the channels can be in open and closed states, and that open close state change can be driven even by voltage changes in case of voltage dependent channels. So how does it work? So let us see that. Okay, so voltage close dynamics of channel is called channel kinetics, or actually gate kinetics, and a lot of work is done on that. But we'll look at the simplest version of that. So people describe the channel kinetics simply as as a chemical reaction. So first order chemical reaction where a molecule A becomes molecule B and vice versa. There's a reverse rate also. So think of the channel dynamics as simply a transition between. So think of open channel as one molecule, a closed channel as another molecule, and this is going back and forth, right? And that you can describe as a chemical reaction, like A becomes B and B becomes A. And you can write it simply using your first order chemical reaction equation like this. So X is the fraction of open channels, let us say, right? X denote, right? Then X is a fraction of open channels. Then 1 minus X naturally becomes a fraction of channels and fraction of closed channels. And if K minus is a reaction rate from, what is this going on? Okay, so K plus is a reaction rate from close to open, and K minus is a reaction rate from open to close. Okay, so then you can write the gate kinetics like this, or channel kinetics like this: dx by t is equal to minus K minus X plus K plus into 1 minus X. Right, and you can define two new terms, x infinity and tau, like this, simply by just rearranging terms in this equation like this. Now the question is again, where does this voltage dependence come? Okay, because we said the channel's conductance is dependent on voltage. Where does it come from? Let's see that. So actually, the way the channel kinetics change, if you look at what is called a patch clamp, And it's possible to actually measure currents of a single channel, and that looks something like this. So this is like a 20 millisecond time frame. And so channels quickly open and close, okay? And people have proposed complicated stochastic models for all that, but here we assume like, only some kind of time averaged responses, and you get a smooth variation of conductance because of that. So how do you get this voltage dependence? So we said that you can represent this channel kinetics in terms of these two parameters, x infinity and tau. X infinity is a steady state value. Tau is the rate at which the steady state value is approached. Okay, given in terms of k plus and k minus. So since conductance is supposed to vary as a function of voltage Vm itself, and since conductance depends on this k plus and k minus, we should figure out how this k plus and k minus can in turn be a function of voltage. And that comes from what is called Archimedes' expression for rate constant. The rate constant itself is a function of this activation energy, which can be linked to the membrane voltage Vm. So that is done here. Something garbled. Okay, so that is given by this. So k minus is given this k naught minus times exponential of minus beta, and V is the membrane voltage. So k plus is also given as a function of voltage like this. So once you express the reaction rates in terms of voltage, then you can finalize the equation. Now, one more small abstraction that Arjun and Exley have introduced is, they said the gates themselves are not monolithic entities, and the channels themselves. Within the channel, they asked us to imagine some kind of gates, right? And given channel is open only when all the gates are open, etc. So the channel variable which we use x, right, has to be replaced by gating variable. Okay, a little bit of abstraction. Basically, they were trying to perfect the data to their experimental observations. So, so by this thing, then the individual sodium channels are supposed to have three what are called activation gates and one inactivation gate, and potassium will have all four activation gates and so on and so forth. So with all this, I won't go into all that analysis, but basically you have two gating variables for sodium. There's M and H, and so when all the gates are open, right, all the channels are open for sodium, then M and H it's like 1. Then the maximum conductance then is given by GNA max, and so think of M and H as probability of opening. So you see that the channel itself is open when all the gates are open, and gate probabilities are given by M, H, and all that. In case of sodium, there are 3 M's and 1 H. So the total probability opening of the gate is product of the probability opening of all the individual of the channel is part of probability opening of all the individual gates. So in case of sodium, you have 3 M's and 1 H. Therefore, the probability opening of the channel itself is a product of all these probabilities. It is M times M times M times H. Okay, and then the sodium channel conductance is given by this probability, which is M cube H, times the maximum conductance, which is GNA times GNA max. So GNA max times M cube H gives you the actual conductance of all the sodium channels put together. Okay, and this M and H dynamics is given by this. This is very similar to this equation. This equation. It's the exact same form. Okay, like that you write equation for the M and H of sodium. And similarly, potassium is supposed to, this is like in sodium channel structure. 3 activation gates and 1 inactivation gate. Similarly, for potassium, you have all 4 activation gates. The gating variable for this is N, and given by this equation. Again, same form. So since there are 4 gates, gate open probability is N, then the 4 gates, the channel itself is open when all the 4 gates are open. That means the channel opening probability is N times N times N times N, is N power 4. Now the channel conductance is basically the maximum conductance times channel open probability, N4, N power 4. So that gives you sodium conductance. Okay, and the sodium gate dynamics is given by this equation. So if you put it all together, right, in the original equation, At the very top, you see the original equation which we started. Now we figured out that GNA can be written as GNA max, right, times m cube h, and GK can be written as GK max times n power 4 because of these two formulae. And now we have three new variables, m, h, and n. Basically, you need all these variables. So what we're trying to do is basically connect GNA to VM. That connection comes through these variables, m cube, m and h for sodium and n for potassium. How does the connection come? M and H have their own dynamics given by this. And inside the dynamics, I have VM coming as a variable. And through these alpha beta functions, which have a bunch of exponentials. All this comes from the Arrhenius law, where these functions are given by this. So it's a pretty complicated model, and the dependence of various variables looks like this. The voltage, membrane voltage, controls alpha beta functions, right, through this formula. Alpha beta functions control M, H, and N, right? Then M, H, and N control the conductances, then which in turn show up in the voltage dynamics equation, master equation. And that in turn, right, controls the VM, and the loop closes. This is the entire loop and all the relationship between all the variables. Okay, now if you, let's see what happens when you inject a small current, I. Right? If you inject a small current, there's only a small blip. So the basic initial voltage is resting voltage is, let's say, minus 70 or something. If you inject a small current, there will be only a small blip and it will come back to the baseline voltage, resting voltage. Now you increase the current a little bit, right, to let's say 0.023 or something. Then at this critical value, suddenly you see the action potential. Right, it will go from minus 70 to all the way to some plus 30 or plus 20 something, plus 30. Then comes back to even below minus 70, and all the things what we described in action potential, you see that here. These are all coming from the same set of equations I just showed. In fact, afternoon you will run this code yourself and verify for yourself. So you see that you will gradually increase input current. Here it is 0.02, and then increase it from 0.02 to 0.023. That's all. Suddenly you see the circuit responding with action potentials. When the AP is generated, you see that the corresponding M, H, and N variables, the gating variables, also show some corresponding changes. So here they're all pretty flat, okay? But once you inject some current, they're suddenly showing some dynamics. All right, and M, H, and N, if you using them, if you construct the conductance by applying this formula, okay, GNA and GK, those conductance values look like this. So you see that sodium conductance, sharp rise and sharp fall, and potassium conductance, it builds up slowly and falls slowly. Okay, so this is what happens when you current is about this value. And you see that when at this current, this is a DC current, it's not a pulse current, it's a continuously given current, DC current. When this happens, you just see a single action potential and it stops again. But you increase current further, some 0.023 to 0.1. Now something radically different happens. Instead of a single action potential, it gives continuously a lot of action potentials. Okay, just like in a real neuron, right? This continuous firing of action potentials. And at the same time, you see the MH and variables also show the same kind of a structure. And the sodium potassium conductance is also the same pattern, but now it's also repeated because the APs are now continuous. Now, as you increase the current further, you see that the frequency of the action potentials also increases slightly, right? But as you increase it further, beyond the point, what happens is the APs start losing amplitude. So you see that in the original case, the AP goes all the way up to some plus 30. But as you increase the input current, the frequency increases slightly, but the amplitude goes down. See that amplitude is almost zero here. As you keep increasing current, amplitude goes further down. So beyond a point, amplitude is so low that you cannot call it an AP anymore. Okay, so all this, if you want to summarize into one graph, the x-axis is the input current, and y-axis is the spike rate or spike frequency. Up to the first threshold, there is no spikes at all. Okay, so there's no frequency. In the first threshold, second threshold, it won't show continuous firing. It will only show like 1 or 2 action potentials and become silent again. So there also there is no real frequency. Frequency means you should have continuous firing. But once the input current crosses the second threshold, then there's continuous firing. And from then onwards, if you keep increasing the input current, there is a constant increase in frequency up to a point. Beyond a point, like I said, the amplitude also starts going down significantly. After that, it's can no more be called an AP meaningfully. So after that, kind of the curve stops there. Okay, this is the response curve of the Hodgson-Huxley model. So in the afternoon, you will actually play with the code yourself and see how it works. Then I will quickly also look at a couple of spiking neuron models. So I think the TS will go through this in the afternoon, but I'll just quickly cover the leaky integrated fire neuron model. So this neuron model basically is RC circuit, right? RC parallel, and then the input current is injected here. The thing is, when the capacitor gets charged, when the capacitor voltage crosses certain threshold, then imagine that the capacitor voltage is just discharged into the ground. Okay, so see how that can be given by this circuit equation. And if you look at the voltage that is of the capacitor, you can give it by this formula, Ri naught into 1 minus exponential minus T by tau. So when you continuously give some current, and if you look at some threshold voltage, right, theta. So frequency of spikes. So basically, imagine that. Let me see if there's any the waveforms. So basically, what happens here when I give a DC current, the capacitor voltage gradually increases exponentially. Once it reaches a threshold, it will get reset, it will get discharged. So it drops to 0 again. Then again, the charging continues. So whenever it gets discharged, imagine that the neuron is emitting an action potential. So in this case, there's no explicit action potential. There's only kind of a notional action potential. So imagine it's emitting that. And now we will have to find out how frequently is it happening? What is the firing rate? So for that, we need to understand how long is it taking for the capacitor to get charged up to some threshold level. So first, let us derive the voltage equation for the capacitor. It's given by this formula 12. Now, this voltage, when it equals some threshold value, let's say theta, right? That's when the capacitor gets discharged. Okay, so from 0 to that value when it reaches theta, that is your time period. That's capital T. So plug it in here and you solve for it, you get this formula. And 1 over T gives you this formula. So in this formula, the input current is I naught. As you vary I naught, let us see how firing rate changes. You'll get something like this. It's actually a log function. It's a very strange, like it's 1 over log of Ri naught by Ri naught minus theta and so on. So first of all, this formula is meaningful only when Ri naught is greater than theta. Otherwise, the argument becomes negative and log is not defined for negative terms. Okay, so that's the first thing. So which means you can have firing only after some threshold value of the input current. Just like the Hodgson-Huxley model. Here also there's a threshold. Okay, now, but then this value can keep on going to infinity as you keep on increasing current, which is not biologically realistic. So they introduced a small change to this formula. They said, so the thing is in a biological neuron, once a neuron fires, it cannot fire again after some time period. So that's called a refractory period. So they explicitly put it into this formula. So T is given by not only this term plus some extra constant term called refractive period or T ref. When you add that, then frequency becomes 1 over T, which is all this. So in this, when you increase I naught as an input current, then the frequency doesn't go to infinity. The maximum value will be like 1 over T ref. So it will actually saturate. So this curve starts looking a bit like the frequency response that you got for Hodgson-Huxley model, right? One thing is in Hodgson-Huxley model, after a point, there is no spiking at all. So the curve ends at some point. In this case, the curve doesn't end. It will asymptotically approach this 1 over T ref term, T ref value. Okay, so this can lead to even further simpler neuron model. So where you just think of neuron as receiving inputs from many other neurons, and think of the inputs having certain weightage Wi. I'll talk about all this tomorrow morning. And it's a completely static neuron model. There are no action potentials, no spikes, no nothing. It's a very simple neuron model. And to get this kind of a step-like shape, people use certain nonlinearities. G can be like a step function like this, right? Or a signum function. Step function goes from 0 to 1. Signum function goes from -1 to 1, right? Or because sometimes you want this nonlinearity to be differentiable. Okay, so for that people use a logistic function. I'll talk about all this later in detail tomorrow. Or it can be, instead of a signum function, you can have, instead of this, I can have a smoother version of this, which is the tanh function, which goes from -1 to 1, but smoothly, it's differentiable. Okay, so we have looked at a very complicated neuron model, which is Hodgson-Huxley, but then we saw the simpler version of it, which is the leaky integrated fire neuron. And even simpler version of it without the dynamics, without any spike generation, which is the static neuron model, which is called the McClelland-Pitts neuron model. So today afternoon, you will be looking at Hodgson-Huxley and leaky integrated fire, and also a couple of other neuron models, which you'll see how to run the code and see how the response looks like. Tomorrow, I'll get back to this static neuron model, and see how you can construct networks using them. So you can do a lot even with the simple static neuron model. And day after tomorrow, again, we'll pick up the same neuron models, like some of them you will be looking at this afternoon. You will get some practical understanding of these neuron models, which are oscillators. And day after tomorrow, I'll look at how to start with these oscillators and construct networks. Okay, so that's all I have for now. Any questions?
Hello, sir.
Yeah.
Yeah. Again, thank you for the lecture, sir. My question is that I'm finding really hard to understand all those equations and terms. So, yeah. So, sir, can you just briefly give the overview and what's the purpose of those equations, if it's fine?
Yeah. Okay, so let me go back to the Hodgson-Huxley model. See, Hodgson-Huxley model is popular because it's one of the first models of neurons response. What is it modeling? It is trying to explain what's the current voltage relationship. So basically, if you have a neural membrane, like given by the circuit, if I inject some current into it, how does the voltage change? That's all. Voltage is a function of current. That's what it's trying to model. And this voltage is in the form of a bunch of action potentials. So the response input is the current, output is the response, which is a series of action potentials. And so usually, if you see these waveforms, the individual action potential shape is pretty much fixed. There's no variation, right? So the only thing that is interesting in the response is the frequency of the action potentials. How many action potentials per second, right? So the input to the model is some current value, output is the frequency. Okay, so that's all. How do you capture this input-output relationship? Now, to understand that, I need to go so deep into all the molecular effects that's happening inside the circuit and so on. So therefore, it is very complicated because they're trying to capture the biophysics of the neuron in great detail. Okay, and at the end of it, you get this same thing, and I can summarize the whole thing in this one curve. Input is the current, output is the firing, the frequency of the action potential. But so subsequently, what we have done is, instead of looking at such a complicated model, we'll just come up with some equivalent model which gives you essentially the same kind of behavior, but without getting into all these biophysical details. I don't care about sodium channels, potassium channels, and right electrophysiology, all that stuff. I'll just give a simple model which gives you the same current to firing rate relationship. This is Hodgkin-Huxley. Is this clear? So a lot of things are happening inside a neuron. What I want to get out of this model is the input-output relationship. What is the input? Current injected into the neuron. Output is a frequency of action potential, some f. This relationship is what I want to know. But to understand that in great detail, I have to write down all these equations. But at the end of it, I just have this curve. Now, what I have done in case of leaky integrated fire neuron is I got the same thing using a very simple circuit model. Okay, in the Hodgkin-Huxley, I had such a complicated circuit model, right? A lot of conductances and batteries and conductances are time varying, very complicated. But see this. That's all. One resistance, one capacitance, and this again is charging by some external current. And then you assume that the capacitor voltage is reset once in a while, whenever it reaches a certain threshold. And then when you look at this firing, the frequency of firing as a function of the input current, and you assume this there is a limit on the firing rate, you get again the similar kind of curve. Look at this curve. Look at this curve. This curve ends here because of all the detailed physiology of the neuron, but this is a even more ideal version where this just goes on to infinity. But gets to the qualitative behavior. Is this clear? I can give further clarification if you ask more specific questions.
Yeah,
Sir,
sir, I get some idea. Thank you, sir. So, just one more thing is that, sir, when you were explaining about Hodgkin and Huxley model, and in that he talked about the multiple gates in a single channel. So, like, why do we include that thing if it can simply be explained by changing of the voltage and opening of the channel? Like, why do we have to include that it has multiple gates?
Good question. I'll come to that. So thing is, we began by explaining that each gate has certain dynamics. Sorry, each channel has certain dynamics, right? And we describe the channel as channel dynamics as simply a transition from open state to closed state, right? This is where we began. You can see the slides, right?
Yes, sir. Yes, sir.
So we began with this, and then we said this is just like a chemical reaction where one molecule becomes another, A to B, and reverse reaction is B to A. Okay, and so that molecule A is open, let's say closed channel, and molecule B is open channel. Then we wrote down these equations, right? And only thing is what happened was when they applied these equations to real channels, it was not explaining the experiment data well. Because channels are so complicated. It's not simply a transition between two molecules, right? Because channel itself is so large protein structures. These equations are not fitting the data well. Then they added one more level of complexity into the model. They said you can't think of the entire channel as one entity which is going between two states, right? You need to think of channel as having multiple portions inside that. And then, see, suppose I have I don't know, can I think of a toothpaste tube, right? I don't know, or think of a long cylinder or a pipe. The pipe is open when every part of the pipe is open, right? That's when you say entire pipe is open. But I can squeeze the pipe at various points. Okay, even if I squeeze the pipe at one point, the whole pipe is closed, right? So now think of the channel as having multiple sections inside that, and where there is independently dynamics going on, the open-closed dynamics going on. This is an abstraction. So in modern protein structures, people don't look at it like this. You do very complicated simulations. Suppose you do molecular dynamics simulations. you will simulate the entire protein dynamics, and you can look at how pore shape changes in 3D. And it's very complicated. But we are talking about, like, all this was in 60s and 50s, last century. They didn't have that kind of understanding of proteins, and they wanted to come up with something reasonably simple. So they proposed this kind of an abstraction. So what they said is, within the channel, imagine there are multiple sections where independently that section is opening and closing independent of the other parts of the channel. And these sections, they call them gates. It's all just an abstract representation. So then, just like we applied all this dynamics to whole channel before, all this stuff, right? Now apply all these equations to single gates, not the whole channel, but single gate, which are parts of a channel. Okay, so that is one thing. Then there is one more dimension which I didn't explain in detail, because all this I take 2-3 hours just to explain Hodgkin-Huxley model in my regular course. So they're actually what are called activation gates and inactivation gates. Activation gates, because these are voltage dependent channels, right? So inactivation gates are those which open when the voltage is increased, and activation gates are those which open when voltage is decreased. So the effect of voltage change on these two gates is opposite. Okay, so then how do you determine when a whole channel is open? Right? It is open when all the gates inside channel are open. Okay, so look at this picture, this schematic. There are 3 gates in it, and the channel is open when all 3 gates are open. Now this gate, initially we talked about channel kinetics. That is all this stuff. Right? All this represents channel kinetics because X represents the fraction of channels open. Now we apply the same logic to individual gates, not to whole channel. Therefore, we now talk about gate kinetics, not channel kinetics, but exact same equation and same form of the equation. But now within this, now we can have a very composite channel where some gates are activation, some gates are inactivation. Okay, and so you do all that. Then now the question is, if I take a given channel, how many gates does it have, and what kind of gates are they? Are they all activation, all inactivation, or some combination? How many are activation, how many are inactivation? But if you ask me, basically it's all a very elaborate curve fitting exercise, nothing more than. Right, and you can, what I will show like today and tomorrow is, you can get a very good models with much simpler equations. Okay, but this is the first model and Nobel Prize winning model. You have to, give it the respect it deserves, and you have to describe the whole thing. But you can manage with much simpler equations, provided your goal is to understand the large scale network dynamics. If you want to study the channel kinetics for its own sake, then you have no option. You have to do all this stuff. So now this equation dx by dt equal to all that now represents the gate dynamics or gate kinetics, and X represents the gate open probability. So if you have a composite channel like this, there will be one X for each of them, so X1, X2, X3, and so on. Now X represents, either you can call it the fraction of open gates, or you can call it probability of opening of the channel. So X1, X2, X3 are all probabilities of opening of channels, gates, which are part of a channel. Therefore, the probability of opening of the whole channel is then a product of the probabilities of opening of all the component gates, right? Because channel is open only when all the gates are open. Okay, so it's product. Now the individual gate the variable M, H, and all, they are governed by this equation. This equation comes exactly from the same original equation, right? All this stuff. So that equation now you apply to single gates like this, right? So this is for sodium. We have 3 activation, one inactivation. I'm sure this is all a part of an elaborate exercise for coefficient. That's nothing more than that. And same thing for potassium. They said there are 4 activation gates. The variable is n. There are identical gates. Therefore, the equation is actually the variable exactly the same for all 4. And the gate open probability then becomes n power 4. n times n times n times n. And once you know gate open probability, channel open probability, you multiply that with the GK max, you get the actual GK, because some channels are open, some channels are closed, and so on. So you get actual conductance by multiplying the maximum conductance with this n power 4. That's all. Once you have that, you have the whole set of equations. After that, it's only calculation. But it's a very messy model, very complicated model. But I'll show you, it's possible to have much more elegant, mathematically simpler models with similar behavior. Any more questions?
Good morning, sir. Can I
Yeah.
have a question?
Yeah, please.
Yeah. Thank you, sir, for this elaborate discussion. I just have a small question that you said like outcome variable is the spike frequency and
Yeah.
input is the
Current.
amplitude of current.
Hmm.
So I just want to know whether the amplitude of current also affects the duration of the spike. I mean, it is just frequency, but how long that spike is going to happen after a input of certain
Okay,
current?
good question. So input is the current amplitude, in sense it's a DC current. Okay, it's a constant current. You see that when I say input is 0.02 microamps per mm square, it's a constant current, right? And then in response to that, if you look at for this low current values, there is no action potential at all. There's only a small blip, right? And then it settles down again to -70. Only when the input current crosses certain value, let's say 0.02 to 0.023, at third decimal you have changed, then suddenly the AP is created. But right now what happens is only one AP is created, after that it becomes silent. So there's no continuous firing. So you increase the current amplitude further. You go up to 0.1, right? Then suddenly you see continuous APs firing. So only now you can define something called a firing rate. Here there's no firing rate, there's only single action potential. Right, and once they are created, the duration is pretty much standard, the shape but as you keep increasing current, the amplitude of the AP goes down. See that here it goes all the way to +30. But when you increase the current from 0.1 to 0.6, the amplitude has gone down to almost 0. Only slightly positive, that's all. Okay.
Yes, sir.
Is
So
it?
my question is, if we increase the current, whether the spike train is going to last longer for
No, this is actually, this is continuous spike train going all the way to infinity.
Okay.
So only in this range, this 0.023 to like about 0.1 or so, you will have a finite number of action potentials. After that, it's infinite spike train. It will never stop. I mean, in the model, in the computation model. In the
So
physical
even if
neurons,
we
that's a
inject-
different story. Sorry?
Yeah, I was asking about the physical neurons, sir.
Physical neuron, it will die after some time. It will burn out, right? If you do it for hours and hours or days and days.
Okay, thank you, sir.
Right? Yeah. Any other questions? So actually, since we have some more time, I'll quickly run through the other single neuron models.
I think there's a question on the chat.
Okay. What is the question? I can't see the chat messages. I don't know why. Can you read
It
it out if
says-
somebody can?
Yes, so
Okay, I
it
can
says,
see it. Yeah.
oh, okay.
Sharing recorded slides, lectures. Yeah. This last one, Harsha, is that the one?
Yes, sir, the last one. Yes.
I have a small question regarding the static models. How do you know and fix the number of variables X? I'll get to that tomorrow. Okay, we'll discuss it tomorrow. Right. Any other question on what we discussed today? Then I'll discuss the spiking neuron models a little bit more. Okay, so look at this. This is called a quadratic integrated fire neuron model. It was proposed by Zikevich, maybe others also, but it's a very simple model. So we have seen the leaky integrated fire neuron, which is given by this equation, right? C dV by dt plus V by R is equal to external current. Now take another variation of this, where there's no C, okay, but because I'm not looking at it as electrical circuit, some dV by dt is equal to external current. There we had minus V by R, so minus V or something like that. Here instead of, that's a linear equation. Here it's a nonlinear equation, so we have V square. Okay, now what happens? Now, so if you just have the first equation, dV by dt is equal to I plus V square, and if I is positive, it will blow up very quickly. Right, V will blow up and go to infinity. Okay, nothing interesting happens. So to avoid that blowing up, what we do is, if V crosses certain peak value, Vp, you reset it immediately. Just like in the leaky integrated fire, we had a resetting step, right? If the voltage crosses some value, some theta, it will reset back to 0. Similarly, here also, we need to have a resetting step. If voltage crosses some peak value of Vp, it will reset back to a certain value, low value, which is V reset. Now, how does this kind of a neuron behave? Okay, so it's very interesting neuron. So look at case 1. So the same equation now I'm just showing it graphically. dV by dt is equal to this. So I plot dV by dt as a function of V. So y-axis is dV by dt, which is I plus V square, and x-axis is the current. Right. So how does it work? So it's a function just I plus V square. Right. This is a plot of I plus V square. Now imagine I is has negative value. Okay, and so actually it should be minus 5. If I is a negative value, then you see that this is a function I plus V square, right? It will be parabola, but minimum value will be at negative, something negative. And that curve intersects the x-axis at 2 points. Right, so y-axis is dV by dt, and this is a x-axis current. So you see that it intersects the x-axis at 2 points, and so if it is so take all the values for less than this first intersection. So in this range, right, the y-axis is positive. That means dV by dt is 0, is positive. Okay, which means if I start from here, voltage goes up, right, and goes up to this point. Now, if I start from any range between these 2 points, in that range, dV by dt is negative, which means the voltage goes down. So if I start some initial voltage here, somewhere here, it will go down, okay, to this value. But if I start from some voltage beyond this range, the second value, then dV by dt there is positive. So voltage keeps going up. So this is a plot of dV by dt as a function of voltage. So you see that voltage will either increase or decrease depending upon the initial condition. If the initial voltage is less than this value, then voltage will increase. If initial voltage is greater than this value, voltage will again increase. But if the initial voltage is between these two values, it will decrease. What that means is the voltage is less than this, it always goes to this value. If the voltage is greater than this value, it will always blow up and go up to infinity. But the resetting step, what it does is, if it, let's say somewhere here there's a V peak. So if it reaches V peak, it is reset back to this V reset value. So in this case, V reset is, so let us give some names to this. So you see that it is always going to this value, which is like a resting state. Right, so let us call this black dot value V rest, that is a resting state. And look at this open circle here. If it is less than this open circle value, it will come back to V rest. But if it is voltage is greater than its open circle value, it will go off beyond that. And if that voltage reaches certain peak value, there should be a V peak here, then it is reset back to this V reset value. After that, it will come back to this thing. So look at the kind of behavior you see here. If if it crosses this value, it will go up to V peak, and then from V peak it is immediately reset to this V reset. After that, which is highly negative, after that slowly goes to this value and stop. Right. So if I start from some value here, I keep rising quickly, and I approach V peak. So I approach V peak. After that, I quickly reset to V reset. That is quick reset to V reset. After that, again I climb up to this value. So I climb up to this value. See, the process is generating a very nice action potential like spike. Okay. So now, so that is case one, right? So this very simple equation can also give you very nice spikes. That's what this equation is showing. Now I'll make a small variation to this and just change the constants, move the parameters slightly and change them to slightly differently. So earlier case, my V reset was less than this V rest, right? So now what we do is I move the V reset to a point which is beyond this open circle. This open circle I'm calling it V threshold, because if your voltage is less than the threshold value, it will come back to this resting potential. But if voltage is greater than threshold value, it will then go further up and produce an action potential. But that's the thing about action potential. There's a threshold effect. If the initial voltage is less than threshold, there's no AP. Only when the initial voltage crosses a certain threshold, there's an AP. That behavior is captured very well by this very simple equation. All this is happening when the current is negative, because only when current is negative, this parabola goes below the x-axis and you have two intersection points. Okay, so now in the second case, I'm considering a slightly different variation. In the first case, V reset is less than the V resting potential. Now I define a case where V reset is greater than even the threshold value, V threshold. Then what happens is like this. If my initial voltage is less than V rest, it will come back to rest. If initial voltage is greater than V rest but less than V threshold, it will again come back to rest. But moment my initial voltage is greater than the V threshold, which is open circle, it will go all the way up to here. Here there is VP. It gets reset. But here in this case, V reset is right here. So it comes back to this value, again reset, again increases further, again reset, again increases further. You see that it's producing an AP and getting reset again and again. It doesn't stop. In the previous model, once it is reset, it goes back to V reset and goes back to V reset and stops after a single spike. So in this case, whereas in this case, once it crosses that V threshold, it keeps on firing continuously. So you see that the Hodgkin-Huxley model is able to show this continuous spiking, right? In one set of parameters for one range of currents. For another range of current, it's only showing one spike or one or two spikes. So this model kind of gives an insight into how that might be happening. It's a very simple model, but gives an idea of how to produce that kind of a behavior. Right. So what we are trying to do here is try to produce the same kind of a complex behavior using extremely simple neuron models. Okay, so this is one example. This is case 2. Now let us look at case 3. So case 2 also, in case 2 also, current is still negative. When you have I plus V square, I is a negative number. Only thing is the V reset have moved from being less than V rest to being greater than V threshold. Okay, then you get this continuous spiking. In case 3, I just have positive current. That means the parabola is now raised above the x-axis, which means for every voltage, my dU by dt is positive, which means no matter where I start, my voltage will be positive. It will be increasing. So it will increase very rapidly because of the square term, and then once it goes to V peak, it will get reset. Here is the reset. So it will keep firing like this forever. Once the current is positive, it will fire forever. There's no stopping. So in Hodgkin-Huxley also we are able to see this continuous firing, right, without any stopping. So you see that behavior here also. Okay, so this simple model gives you a lot of insight into how all these behaviors that you see in more realistic, biologically realistic cell neuron models. How do you get all that? You get some insight even with the simple neuron model. So actually, if you look at even the waveform, you see that this slow increase and again a bit of slowing down, again a rapid increase. Real APs actually look like this, right? In fact, if you make the current only slightly positive, then this AP actually looks very interesting. It will have a very flat stage and then a plateau-like stage, and then it goes to a max and comes down. You do see those kinds of action potentials in other cells. For example, in cardiac cells, you do see those kinds of strange-looking action potentials. And all those features can be obtained using this very simple neuron model. This is called a quadratic integrated fire neuron model. By just playing with these parameters, you can get all these different kinds of APs. Now let us look at a slightly more complicated neuron model. It is again a quadratic integrated fire neuron model, but with two variables. Okay, this equation is on the single variable B, and Hodgkin-Huxley has 4 variables if you remember. There's a very complicated model. Alick integrated fire has only a single variable. Now we look at two variable model. To understand logic of these two variable equations, so we need to look at what is called phase plane. I will do all the phase plane stuff day after tomorrow. And then followed by that, you will actually be doing phase plane analysis, and you will learn to use some software called XPPOT. All that you will do on day after tomorrow afternoon. But for now, I don't have time for all that. I'll do a separate session on the day of tomorrow. But these two variables look like this. d by dt is equal to this minus u plus u min plus p into b minus v min whole square. The second equation du by dt is equal to minus u plus s into v minus v square, no, v naught. Okay, so if you, and these two equations then can be further simplified to this form. Equation 3 and 2, sorry, it is 3 and 4, should be 3 and 4, can be simplified by redefining variables like this into 7 and 8. Okay, you get this. And you see that in this form, these equations only have 4 parameters or 4 constants, ABCD constants. And what is interesting, this is proposed by a guy called Eugene Izhikevich. And just by playing with these 4 constants, you can make this neuron model show all sorts of behaviors, as you can see in this picture. Okay, so look at the first one. It's called tonic spiking. That means for a constant current, the neuron produces continuous spiking. It will go on until infinity, it's continuously at a fixed frequency with regular spiking. Now, if you change the parameters ABC a little bit, the same neuron, the same current, right, now will only produce one spike and become silent. So we saw this kind of behavior in Hodgkin-Huxley model, right? For low currents, it will only show one spike and stops. And you see that happening, right? Again, same equation, but vary the ABCD constants slightly differently again. Now we see very different behavior. This is called tonic bursting. The first one is called tonic spiking. Second is tonic phasic spiking. That means phasic means only one or few, not infinity, but spiking. In the third case, it is called tonic bursting. Bursting means, see the burst here in the example D. There are a lot of action potentials which come at a high frequency and in a bunch. That's called a burst of action potentials. In case of tonic bursting, you have many bursts coming periodically. That means that the neuron fires lots of APs, becomes silent for some time. Again, lots of APs become silent for some time. Right? Again, the same equations produce this behavior, but only for at different values of ABCD. Current is same DC current. This is called tonic bursting. Then again the same thing, but different values of ABCD. Instead of continuously bursting, it shows only one burst and becomes silent. That's called phasic bursting. And then for a different set of ABCD, you get mixed mode. So you see that in this case, for the same current, the neuron shows one burst followed by a bunch of spikes. So it's a combination of bursting and spiking. Okay, so like that, by varying this ABCD parameters, you can get all sorts of behaviors. It's a very rich model. So what I'm trying to show is, see, look, compare this with the Hodgson-Huxley model. Hodgson-Huxley model has 4 variables and very highly nonlinear equations, almost impossible to do theoretical analysis, right? But look at this equation. And the Hodgson-Huxley model, the nonlinearity is all transcendental functions, exponential functions and all. It's extremely complicated. But look at these equations, just quadratic nonlinearity, right? That's the highest nonlinearity is quadratic. And you have all the resetting steps, of course. If p is greater than some 1, it's reset to c. And if u is, and at same time, u is reset like this. U is reset from u to u plus d. Okay, the resetting is there. But otherwise, it's a very simple set of equations, and you see such rich dynamics. So this is where you see a stark difference between real neuron models, biologically inspired neuron models, and the AI neuron models. In AI neuron models, you have, as we'll see tomorrow, right? You just have either a sigmoidal neuron or a ReLU neuron and decay ReLU and all those things. First of all, there's no dynamics at all. Secondly, look at the biological neuron. This is not even very biologically detailed neuron model. It's a very simple neuron model, but look at the richness of dynamics. 28 different firing patterns all coming out of the same equations just by varying the parameters. And even all these 20, there are real neurons showing all these behaviors, right? So it's not just some mathematical abstraction, but they're all real. So neurons do exist. Now, the big question is, why do you have so many different kinds of neurons? What is their contribution to what kind of specific computations they are doing? All that we still don't know. We don't know because we need to construct networks of such neurons and study what is special about them and so on. That kind of work is, to my knowledge, not yet done. Okay, so it's a huge, if you compare the AI networks and with this kind of a detailed or bio-inspired neuron models and potentially the networks you can construct with them, the amount of research that you can do is like just immense. But it's important to know that there are neurons like that, and you can describe them using fairly simple equations. Okay, so then we will, I think, afternoon there also look at other neuron models like Fujinagoma model, which is a reduced version of Hodgson-Huxley model, and then Morris Lecar and all that you will do. And on Wednesday, like not on Monday, I'll look at phase plane analysis. In that context, I'll look at limit cycles and I'll show you how to model such neuron models using limit cycle equations. Okay, any questions? Questions?
Hello, sir.
Yeah.
Yeah, this might be a little dumb to put it plainly. Is it necessary to understand everything you said, or just the concepts are enough to understand what's coming next?
No, depends on your objective ultimately. Now,
Okay.
suppose you are a research scholar doing research on different kinds of neuron models. For example, Izikevich has written a whole book on this kinds of neuron models.
Okay.
We'll give you a reference to that if you want, dynamical systems, neuroscience, something like that. It's a beautiful book. Suppose your research involves studying such models, then you have to know all this. But depends on your overall objective of research, right? You just want to have a general feel for what kind of neuron models are there in neuroscience. This is a quick glance is enough. You don't have to remember all the details. It's enough you know that such things exist.
Okay.
But
Okay.
some people study, for example, I don't know if you are a, let's say, experimental neuroscientist. You are studying some special neuron in some animal. You want to understand its responses. Then you have to construct Hodgkin-Huxley type model with ion channels and all. And if you are studying single neurons in great detail, then you have to look at compartment models. We are not doing that in this course, and that itself can be a whole conference or workshop by itself. then that's a whole different ball game, right? For a single neuron, sometimes people even build such large models that you need some 500 compartments for a single neuron. People do that. If that's your research, then you have to do all that.
Okay.
But personally, I'm not interested in those kinds of models. I want to understand brain at large scale, but understand dynamics, right? So that you can understand diseases and what happens to the brain and disease conditions at large scale. Then you may not need all this stuff. It all depends on your ultimate research objective. Everybody's goals are different. So we can even go to even more detailed levels, but that's not the scope of this workshop. If there are people who study all that, that can be a whole different workshop altogether. You can look at effect of chemicals on neural firing. All that is very different study. But the phase plane methods, which we will introduce on the third day, they're very fundamental and quite useful. We want to study oscillators because oscillators is a big, we're emphasizing oscillators a lot in this workshop. And third day, we'll start discussion of oscillators.
So, sir, is there a specific model that usually preferred more than the other when it comes to neuron models?
So the thing is, there are broadly two types of neuron models: static and dynamic. Okay, the static ones are the ones which you use in AI and deep networks and all. These are your McClelland-Pitts neuron model, your sigmoidal nonlinear. They're very super simplified. But there are more in use more in AI domain. The moment you go to neuroscience, you have to talk about dynamics. Here there are again broadly two subcategories. The spiking neurons, right, which is the leaky integrated amplifier and that kind of thing. The other category is not even, there are oscillator neuron models. That means the equations are quite different. In fact, when you talk about oscillations, you typically mean the dynamics of not single neurons, but groups of neurons, what are called neural ensembles. That is the average activity of many neurons. You can describe it as an oscillation. And you think of that as a basic unit of computation in the brain. Don't go all the way to single neuron level. Just look at a whole bunch of neurons. Look at their average activity. And that will be like a nice smooth oscillation. So talk about brain's computations in terms of such oscillation, right? That is the other kind, the two kinds of dynamics.
Okay, sir. Okay,
Right.
thank you.
So people keep on studying spike neurons also. If you want to do that, you can do all the things that I've talked about just now. In the afternoon also, you learn about spiking neurons. But in this course, in this workshop, we want to emphasize oscillations, because that's then with that kind of networks, you can easily generalize them to deep networks. You can have deep oscillating neural networks. They're very powerful. You can construct deep spike neural networks also, but they're very painful to train. People have a lot of difficulty training them. But if you go to deep oscillating neural networks, they're very powerful. So you can train them very well. That's the main emphasis in this workshop.
Okay, sir.
There's a chat box question. What was that?
So there's one more question about
yeah.
linking behavior.
What kind of experiments helps us to link these neural dynamics with behavior? And also, okay, linking neural dynamics with behavior means you need to have a network. Behavior means you need to have a network. That network can be a spike neuron network, which we are not going to do in this course. Charita will do a little bit. I think she is simulating a network of spike neurons to produce epileptic activity and all that. Otherwise, that's not emphasis in this workshop. The other kind of network is oscillator network, where we'll show how to we'll study the dynamics of single oscillators We'll also train the network and on large data sets and show how you can explain behavior. We'll be doing that also again using deep networks tomorrow. So like that, you can link behavior with dynamics. One more question. Oh, thank you. Any other questions? I think a lot of questions will be answered when you do the practical sessions, because you can play with the code yourself and that will give a much better understanding than just listening to the lecture. And actually what you can do is after the practical session, then tomorrow again you bring up the question, right? You'll have more clarity. I want this to be interactive, but that's the whole point of having, attending a live session. Okay, any other questions? Because no questions, shall we wrap up the morning session? Wait. Okay, the linear model feels like walking up a ramp, but the QAF model has the square term. Does the square we basically act like boost that? Yeah, actually, very good point. Very good. So in the linear model, what happens is the charging pattern is like very slow and smooth, like like a exponential. Whereas that's not how a real AP. In fact, in the linear decay integrated fire neuron model, it doesn't model the action potential itself. It's a very abstract model, very simplistic, and not at all not realistic. Whereas in the quadratic integrated fire neuron model, moment you go from linear to quadratic, some magic happens. Moment you go to quadratic, the voltage buildup shows that rapid buildup to a peak. And when you reset, it falls to the reset value immediately. So it actually looks like an action potential. There's an explicit action potential generated in the quadratic integrated fire neuron. Whereas in the LIF neuron, leak integrated fire neuron, there is no explicit action potential. When the capacitor voltage reaches the threshold value, you just imagine that the AP is generated and you reset the voltage, but there's no explicit AP. The capacitor voltage doesn't look anything like the AP. So a pretty weak model in that sense. Yes, you have made a very good point. Yeah, the acts like a boost that simulates sodium potassium sodium channels. You can think of it like that. Yes. You can do a lot of things with that leaky quadratic integration fire and also the Izhikevich two variable model. We'll give you the code with the afternoon MATLAB code. You can play with it. It's extremely rich, unbelievably rich. Okay. Any more questions? QA model is not harder to build. It's just one term is different. That's all. It's so simple. But the behavior is already so rich. In fact, I didn't have time to elaborate. So one of the case two shows bistability. That means It's coding in MATLAB Python. Okay, Python. But I thought the SQH model is in MATLAB. I don't know. Maybe there's a Python version also. I think the TS will know that better. QF model is very simple. It's just one term is nonlinear, quadratic. That's all. More questions? Okay, if there's no questions, wrap up. Let's wrap up this morning session. Then let's meet again at 2 o'clock, right, Sundari?
So 2 o'clock.
2 o'clock for the practical session. So,
Yes, sir.
yeah, hope. Good luck. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.